Okay, this is the question 13. I rushed it to try and get it in at the end of the lesson and it didn't work out. So I just want to go through it again and do a bit of a deep dive, actually, because the time I had just didn't work out. So here's your question. There we go. And here are the valid bits from the data sheet. So I'm going to work through this now. So I might have to go up and down a bit, but stick with it. Calculate the electric potential at a distance of 1.5 from a point of charge minus 0.48 nanocoulombs. So, electric potential. Can I draw on this? No. It's basically VE equals KQR. So I'm going to write it again here. So my K, and I'm just writing this for good order, is 8.99 times 10 to the minus 9. No, sorry, plus 9. My big Q in this case is going to be minus 0.48 nanocoulombs. And the R, well, I'm going to do a diagram first to start off with. So this is what we're talking about. R heading in this direction. This is the electric potential heading in this direction. And because this is a 1 over R, I'm going to have that sort of shape. And what I need to do now is figure out what it is when R equals 1.5 meters. And that's going to give me a result for VE, which is the potential. I'm going to actually write there 1.5 at 1.5 meters. And that's going to be a negative number, but that shouldn't be a surprise because that doesn't have a sign, but that does. So that negative sign is going to be carried through our calculation, so it's going to get a negative potential. So again, repeating, VE equals KQ over R. I'm now going to put in those numbers from earlier. It's 8.99 times 10 to the 9 times by, and I'm going to put my negative sign there very explicitly, 8 times 10 to the minus 9, because that's how I'm going to do it in my calculator, divided by 1.5. And that gives me an answer. And again, this is important. Minus 2.8768, and this is volts. The answer for that calculation is going to be 2 sig fig. I think everything in the book is 2 sig figs. So I'm going to write that as 2.9 volts, but I'm going to carry my calculation through with those extra digits just to be on the safe side. So now, so this is just the potential around this 0.84 nanocoulombs. Okay, that's what we're thinking about. So now we're going to be introducing in other elements. So if we go back, so now we're B, and in one case we have so let's do our diagram in case of B1. So you've got a negative 0.48 here, and you have well actually it's a bigger charge, which is a bit weird, minus 1.3. Both of those are nanocoulombs. So actually when you think about it, the force is repelling them because they're both negative and negative. So if I want to bring it in from infinity into there, I will have to work against the repulsive force, and so I'm doing, positive work. So my number is going to be positive when I bring it in, if you like, from infinity. So I can work this out in two ways. Like most of these things actually. I can just go EP equals K Q1 Q2 over R. I go up here, there we are, that's the top one equation there. But also, what I'm really saying is EP is equal to K Q1 over R times Q2, which is essentially VE times Q2. So what I can say is that my electric potential, and this is the one where I'm looking at 1.3 nanocoulombs, is equal to my minus 2.8768 times by my minus 1.3 nanocoulombs. If I put that into my calculator, I get plus 3.7398 times 10 to the minus 9. Spot the deliberate mistake. There's the minus sign there, the minus sign there, minus, minus, positive there. And again, this matches with our idea of going from zero, having to do work against my repulsive force. So I'm essentially storing force into the system. It's almost like I'm pushing or stretching a string, or even compacting a string. Sorry, I should say spring. But the maths give you, it's a negative here, negative there, you have a positive there. The next one, 0.90 nanocoulombs, and this is a positive. So again, you could do it by plugging in the numbers into K, Q1, Q2 over R, but the quicker one is just to say the energy at 0.90 nanocoulombs plus is going to be minus 2.8768. That's the potential, 1.5 meters, times by my plus 0.90 nanocoulombs. So again, minus sign, positive sign. I'm going to end up with a negative sign there, which is equal to, what happened there? Sorry. Point 589 times 10 to the minus 9 joules. Sorry, I should put joules there. So in this case, there is an energy stored in the system to go from here. you would be you're basically saying that the potential energy of the system, to get it to infinity, to zero, you'd have to do work. And that's the idea that you have a negative charge here, and you have a positive charge here. This is my plus 0.90. So to take this away to infinity, to get to zero, the only way I can be doing work to get to zero means I must be starting in negative numbers. Indeed, that's the case. So if I want to pull my 0.90 nanocoulombs positive charge away from this negative charge, I'm going to have to do work. But if I separate it out to infinity, I'm still going to be at zero. So that's the idea. And I'm going from minus 2.6 times 10 to the minus 9 joules up to 0. Means I'm doing 2.6 times 10 to the minus 9 joules to get to 0 at infinity. Right, I notice my handwriting starts to get bad after a while, but I'm going to keep plodding on. So, now it says C. For each of the charges in part B, calculate the work needed to change the separation of the system to 0.58. Okay, so here let's have our minus 0.48 nanocoulombs. You've got another one. We start it over here at 1.5 meters, and we're trying to take it to 0.5 meters. So that means I'm going to have to take my minus 1.3 nanocoulombs. And this is a repulsive force because they're the same size, so there's going to be a force acting in that direction. And so to do that, I'm going to have to overcome work, so I'm going to be doing work. This should give me a positive answer. Because I'm going to have to push to get it here. Anyway, I don't want to do that. So there's lots of ways I can do this. So I can go back and I'm going to do this sum in two ways. So the work done is going to be basically the change in potential energy. So remember our EP is equal to K Q1 Q2 over R. So my delta EP is going to be E final minus E initial. So this is the same as my work done, because if I'm changing potential, that's what it is. So it's going to be K Q1 Q2 over R final minus K Q1 Q2 over R initial. Okay. So what we're going to say is that is K Q1 Q2. I take that outside the brackets, divided by 1 over R final minus 1 over R initial. Which is K over Q1, Q2 over 1 over 0.5 minus 1 over 1.5. If I plug those numbers in, I get a plus 7.48 times 10 to the minus 9 joules. And that's what we expected it. The key thing here is that positive sign. Because here, I'm taking a negative charge. This is going to be repelling it. This is the force of repulsion. So I'm working to bring it closer. So I'm storing more energy in this system. Okay, so that gives me a plus 7.48 times 10 to the minus 9. However, there's another way of looking at it. All the way back. W equals Q delta change in potential. Sorry, Q times change in potential, electric potential. So what I can do is use that. So this is C2 now. So I'm going to use a separate technique. So I have VE at 1.5 already. That is minus 2.8768. So now I do my VE at 0.5. So what we can do is that we can do the sum. VE is equal to K, K times minus 0.48 nanocoulombs all over 0.5, which is equal to 8.99 times 10 to the 9 times by 0.48 times 10 to the minus 9 divided by 0.5 gives me an answer of minus 0, because I've got a minus sign there, sorry, sloppy, minus 0. Should have been a minus sign there. We get minus 8.6304. That's just through doing the calculation. There is another way of doing that. So this is like a slight deviation. What you could say is VE is proportional to 1 over R. R is going from 1.5 to 0.5. So actually, as this is getting 3 times as small, our VE will go 3 times as big. And actually, if you do the sum of 8.6304 divided by 2.8768, it is indeed 3. But of course you can just work through that calculation to get to the potential volts at 0.5 meters. So what does that mean? So we go back and look at this sum. Our delta VE is equal to, what was it, final minus V initial. This is where the minus signs get quite complicated. So it was minus 8.6304 minus 2.8768, which gives us an answer of minus 5.7536. So now we go in and we say that our work done is equal to minus 5.7536 times by the charge. In this case, it is, we've changed this to be 0.90 nanocoulombs, and it's a positive, will give us a negative answer, which is minus 5.178 times 10 to the minus 9. Now, what does that mean? In this case, we were taking, we had a negative, excuse the lack of nanocoulombs, and then you have a positive, and we were going from 1.5 meters to 0.5. So actually, rather than having to work against a force, like the repulsion force earlier, it's actually being pulled in. So you're not doing work to get it there, you'd have to do work to get it away. So this is why we're at minus 5.178 times 10 to the minus 9 joules. Because here, there isn't energy being stored in the system, it's the opposite, it's going away. So there's less energy here than there is here than there is there. And that's why you've got a minus 5.178 times 10 to the minus 9. So anyway, that was a slightly different approach. But we got, for C1, we got plus, and for C2, we got a minus. But what I'm going to do now is do C1 again with this new way of doing it, which is saying it's Q times delta VE. Now our delta VE is the same because we're going from 1.5 to 5. So delta VE is equal to minus 5.736 volts. Here, our charge is equal to minus 1.3 nanocoulombs. Now, our work done is equal to minus 1.3 nanocoulombs times by minus 5.736, which gives us an answer of 7.47 times 10 to the minus 9 joules. Negative, negative. That's positive, which actually does match what we did here. Okay, there's a tiny difference because of the way we rounded numbers, but essentially you'd make that 7.5 times 10 to the minus 9. Oops. 7.5 times 10 to the minus 9 joules. And again, positive, positive there. So they're the same answer. So you can either think about what's happening with these positives and negatives, or just work through with your formulas and be very, very conscientious about whether things are plus or minus. So I was trying to do that there. But that's the key. For these ones, oops, use positive and negative very accurately. Okay, there we go.